Thank you very much for the introduction. Yeah, my name is Valeria. You can call me Lera. That's less formal. I prefer that, if you're cool with that. So today we're going to discuss post-quantum blockchains, quantum computing. This is an exciting topic. I know it was prompted by your questions, so you get the message here. The more technical questions you ask, the more technical talks you're going to get, probably. But feel free to jump in with questions. If you have any, I'd be happy to answer them as we go. I think this audience, as no other audience, would probably appreciate this topic because it's very futuristic. We'll be looking far ahead into the future and how the world of computing is going to probably be changing, governed by new laws of physics. So it's kind of exciting. But it has implications on the blockchains that I'm going to devote a lot of time speaking about, and what can we do to protect our blockchains in the post-quantum world. So I want to start with kind of scaring you a little bit. You can argue that today, blockchain attacks could have been prevented. Typically, we look at how the attack has happened, and we know what exactly was the problem and how it could be avoided. So it could be maybe an implementation bug. Maybe there is an error in the code that got exploited. Maybe it was a bad design. Maybe cryptographers didn't do a good job. Maybe they didn't prove the protocol secure, and it was exploited that way. It could have been also that the protocol was not decentralized, that there was, in fact, a centralized party who was taking too much control over the protocol, and this party got corrupt or hacked. That's also a typical scenario for blockchain attacks. There are many others, but the type of attacker I want to talk to you about today is kind of a larger adversary. It's not operating yet, but it's kind of lurking in the future. It may come about, and we will discuss what are the implications that it's going to bring. So the adversary is a quantum adversary. I kind of drew this gloomy picture when quantum computers come about, that the world is going to be that gloomy. It doesn't necessarily have to be the case, and I'll try to convey a more optimistic view around quantum computing and what kind of new realms it can bring for us. As computer scientists and engineers. So the main problem with the quantum adversary for our setting, for blockchain developers, is that quantum adversary can break our blockchains in three main different ways. Really, there are just three problems that we have to deal with if we are worried about quantum attackers. The first is an implication of the fact that quantum attackers can forge currently used digital signatures. So all of the digital signatures we use in our blockchains and all the internet today, they're quantum attackable. We know efficient quantum algorithms that can forge those signatures. So those are all the signatures we love: BLS, ECDSA, EDDSA, you name it. So if an attacker can forge digital signatures, it means that, first of all, it can steal funds. It can just try to move funds out of honest users and into his own accounts. So that's problem number one. Problem number two is that it can fork proof-of-stake consensus. It can break validator signatures, pretend to be impersonate the validators, and just create an alternative fork of the blockchain, either disrupting the blockchain, do double spending, kind of disrupting the ecosystem. That's a problem number two. And the less of a known problem, and only recently people have started discussing it, is the implication for Bitcoin, for proof-of-work puzzles. Turns out there is a slight advantage that the quantum attacker is going to have in solving proof-of-work puzzles, and that might cause centralization of proof-of-mining power around the quantum adversary. So it will kind of push away classical miners, and probably will be in the world where only quantum miners are going to be supporting the Bitcoin. So let me give you an outline of what we're going to talk about. So first, I will explain what are the quantum technologies, and I'll focus on three main topics here: quantum channels, quantum annealers, and general-purpose quantum computers. Those are the main three kind of technologies you're going to be hearing about when you read the news or when you research what quantum computers are. People are talking about either of these three. Then I'll show you what's the progress in general-purpose quantum computers and how we can extrapolate it to figure out when we're going to get a large-scale quantum computer. So we'll see what's the current size of a quantum computer and how it's been growing for the last 5 years. Then I will focus on the blockchain and why quantum adversaries are a threat. we'll go into more depth on all of these problems I just mentioned, and then I explain how to defend our blockchains, how to make them more secure so they're not susceptible to quantum attacks. And I'll show you a hint, kind of just a glance at new cryptography that is being developed and deployed, and I'll explain how to deploy it to protect the blockchains today. All right, so I want to start this main body of the talk with a quote from Richard Feynman, who was saying that nature isn't classical. So last century, we figured that nature is quantum mechanical. So if you want to make a simulation of nature, you'd better make it quantum mechanical. And I think it's a very inspiring quote because classical computers are kind of boring things. You know, those are just 0, 1s, and you do some basic operations with those kind of classical analog bits. But in quantum world, you can do much more fascinating stuff. And you know, in the world when we have dark matter, black holes, all these different quantum effects, when you start looking at the world at microscopic level, it's kind of would be very interesting and inspiring to bring this new laws of nature that we just discovered and make them serve computer science so that we can either simulate the nature or we can maybe use it to help us discover new laws of nature. Or, you know, the possibilities here are endless. So that really opens up like a new door for computer science, I think, to just look forward to, possibly. So let me start with quantum channels. Those are the simplest quantum techniques you're gonna see, and they're nothing fancy. They're already practical today. So quantum channels are used for private communication. You can, if you have a quantum channel, you can do secure communication with very minimal cryptography. If you look at secure connections we do on the internet today, for example, if you go to your website URL, yeah, you do an HTTPS connection. If you look at the amount of cryptography that's happening there, it's insane. You have digital signatures, you have public encryption, you have message authentication codes, you have symmetric cryptography, hash functions. I mean, there are tons of stuff going on. It's a very complicated protocol just accessing your bank's web page. But if you had a quantum channel between your computer and your bank, you can do secure private communication with very minimal cryptography. It's unconditionally secure, assuming you have authenticated classical channel. I won't go into the great depth there, but things become more simpler. And when I say quantum channel, I mean nothing fancy here. A quantum channel is, for example, just free space communication. So if you have on-Earth station and a satellite flying in the sky, and you have direct visibility of this satellite, that's a quantum channel. That's it. You can shoot polarized photons from your on-Earth station to the satellite. That's a quantum channel. Or if you have fiber optic channels between on-Earth stations, that's also a quantum channel. And there are companies building businesses around providing functionality of quantum channels. And recently, quite recently, 5 years ago, China made an experiment where they established a secure connection between Beijing and Vienna. I think that's current record for the distance at which you can establish a secure channel using a quantum channel through Chinese satellite. Okay, so that's the simplest quantum technology we kind of already start to have in the real world. Another interesting technology is quantum annealers. Those are special purpose quantum computers, and they are used to, for optimization problems. So here, an interesting quantum effect is exploited that the quantum system aims at minimizing the energy. So it always will tend towards a lower energy state. So for example, if you're trying to minimize the function, if you end up at a local minimum and there is a better local minimum nearby, the quantum system will kind of slowly move to that other better local minimum to the right. That's easier with the quantum systems. That's much harder with classical systems when we have gradient descent. If you want to find another local minimum, you have to start all over again from the top of some hill and kind of going down. You may not end up in a global minimum, but with quantum machines like quantum annealers, that can be possible. And the potential use here are, the main one is training deep neural networks. So you'll be able to find better solutions for your optimization problems there, or do drug discovery, protein folding, D-Wave Systems is a company to kind of that's trying to build quantum annealers, and they are pioneers in this space. There are a lot of controversies around D-Wave systems. Every time they make an announcement, there is an army of academics trying to discuss whether their claims is true. It's kind of an interesting debate to keep an eye on. And finally, quantum computers. Those are the technology we are really hopeful for. Those are going to be general purpose, solving general problems. So if you've seen a quantum computer before, it's kind of this chandelier, typically, that hangs from the ceiling. And in fact, the quantum computer itself is just a small chip that lays at the bottom of this chandelier, and the whole chandelier is just a cooling system, and it dumps vibrations. So all it does, all these fancy golden wirings, they're just cooling the tiny chip at the bottom. And the size of the quantum chip is not much larger than the size of our laptop chips. So because of this kind of complicated cooling that has to happen to create this pristine environment for the quantum chip to lie in, it's unlikely that quantum computers are going to be embedded in our laptops, or it's unlikely we're going to have personal computers. Those are going to be cloud-based. So we'll have a bunch of personal laptops kind of connecting to a quantum computer over the cloud. So that's good news, because it means we still have to develop classical cryptography, and classical machines are still going to be in use. Not everything in the world is going to be replaced by quantum computers if we're going to build them. So they are likely going to be just used for hard computational problems that you can just send over to them. They will compute the solution and give it back to you. OK, so where's the power of a quantum computer coming from? It's kind of complicated to explain. I won't go into great depth, but I give you a hint at why quantum computers are more powerful than classical. And the power is coming from the qubit. So if you look at our classical bit, it can only take two values, 0 or 1. Occasionally, the bit can give errors. If there's a cosmic ray hitting it, it can jitter a little bit, but more or less it's just two values, 0 and 1. Qubit, on the other hand, can take a whole spectrum of values. In fact, the qubit state can be anywhere on the sphere, or on the circle, in a two-dimensional space between 0 and 1. So it's a superposition of the two states of 0 and 1. And because qubits can take this whole range of values, they're kind of more expressive. You can already see that they're more expressive than typical bits. The most promising technology right now to instantiate a qubit is superconducting circuits. That's what IBM is using. You can also do trapped ions, photons, but those have to be really tiny, and those have to be cooled down to absolute zero temperatures in order to exhibit the quantum effects. And if you can apply transformations to your qubit, and what's going to happen underneath the hood is you're going to be applying your function f to both values, 0 and 1. So if you start with a superposition of 0 and 1, and you apply the function f, you'll end up with a superposition of f of 0 and f of 1. So for one qubit, you can compute f at both values at once. Okay, you apply f once, but under the hood, you're computing it twice. If you go to more qubits, so if you look at two-qubit system can be in superposition of 4 states, yeah, all possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Those are 4 values. Two-qubit system can be in superposition of 4 values. When you apply the function, you'll end up applying it to all 4 possible values under the hood. And if you go to a larger qubit system, like n-qubit system, you'll be computing on 2 to the n possible combinations of this bit values. Okay, so this is really where the power is coming from. And under the hood, you're computing the function on exponential many values, while you only do apply this function once, effectively. Quantum computers, so though there's this exponent there, it's kind of, it's not straightforward that they give exponential speed up. In fact, they're not, but they are really great at helping us understand the properties of the functions. That just because they can evaluate the function at many, many values all at once. But this is really where the power is coming from. OK, so let's see what's the progress in quantum computing in recent years. So here you have a growing quantum computer. You see how the number of qubits grows over the last years, and In particular, I want you to look at the last 5 years. So IBM in the US is pioneering the space. We also know that China is building a quantum computer, but we don't have public announcements around that. So IBM numbers are really promising. The last 5 years, the number of qubits are doubling. And this year, they plan to announce a 1,000-qubit processor. So I would say if it continues to double each year, we can call this progress quite rapid. So there are two main quantum algorithms that you should be aware of, and every time you read about quantum computers, you will see the mentions of these two algorithms probably. Both are from the mid-90s. There's Shor algorithm and Grover's algorithm. Shor algorithm gives you efficient way to factor numbers and to solve discrete logarithms. And that's the reason why our today's cryptography gets broken, just because Shor invented this really efficient algorithm for factoring and finding discrete logs. And Grover algorithm improves the search problem. So that has some implications for symmetric key cryptography and hash functions. I'm going to talk about it a little more in just a second. So let's focus on Shor algorithm just because that's the most important algorithm for blockchains. So for Shor algorithm for factoring, if you have a large number n that is a product of two primes, to find the factors, to find p and q quantumly, you only need to spend polynomial time. So the length of n to the degree 3 operations on quantumly, and classically, we don't know anything better than number field sieve, which takes exponential number of operations. So quantumly, you have a polynomial time algorithm, but classically, we only know how to factor in exponential time. So the implication is that we know RSA would be quantumly broken. And RSA certificates are 90% of the internet. Okay, so if you go to any website, if you click this green lock button next to the URL in your browser, you look what certificate they use to secure a connection, it's likely going to be RSA certificate. So if RSA gets broken, we are in big, big trouble. And the rest of the certificates are kind of discrete log-based, and turns out Shor algorithm generalizes to discrete log-based certificates as well. So basically, if somebody builds a quantum computer today, the internet is gone. Okay, so I just want to take a moment and for you just to imagine this world, like what it's going to be like. So in the presence of a quantum computer, today internet is completely insecure. So what it means is that you cannot access your bank web page. Banks cannot do financial transactions. The blockchain stops working. You can't send secure messages. You cannot even, upload the update to your machine to fix it, to make it quantum resistant. So it's really, really devastating. We hope nobody is building a quantum computer kind of in private right now, and we really hope that nobody will just show up with a quantum computer all of a sudden. So quantum attackers will be able to read all the traffic and impersonate anybody on the internet. All right, so that's kind of a gloomy view of the world. Let me show you a little bit more optimistic view. So the largest current processor has 400 qubits. But how many qubits do you really need to break cryptography? Well, it turns out you need a lot more. So, for example, you need 20 million qubits to break RSA and 13 million to break elliptic curve Diffie-Hellman. So you see this gap is quite high. Okay, we only have 400 and we need 13 million. But the number of qubits seems like it's doubling every year. So if it continues along the same lines, if it will continue to double every year, this gap will be breached in 15 years. So that's kind of enough time for us to prepare, probably, but it's kind of a short amount of time that we might, want to keep an eye on this and the progress that we have here. Great. So I want also to highlight a recent paper that came out last year, December 2022, that were saying that they figured a new algorithm to break RSA, and you can now run it on an existing quantum computer. So it only requires 372 qubits to break RSA. And it caused a big hiccup of the community, like everybody was suddenly in panic. People started analyzing the paper, seeing if the claims are really true or not. And after a while, a few weeks have passed, people concluded this paper has some problems, that the claims are not quite true, and the RSA is still secure. And Peter Shor, in fact, is quite active on Twitter. If you want to follow him, that's the author of the algorithm that breaks RSA. He was saying that this paper apparently has problems. But it might be the case that as we go, we see more and more results like that, and we might better think about how to prepare ourselves just in case some of this result turns out to be true. And even if you're on the skeptical side and you think that the probability of building a quantum computer is small, just think about the huge devastating effect that it's going to have on our world and our society. So if you multiply this tiny probability of building a quantum computer with tens of millions of qubits, if you multiply it by this huge effect that it's going to have, maybe the probability won't seem so small anymore. But I want to just for a second take the side of the skeptics and say that from quantum mechanics, we know that when we have few particles, when the particles are really tiny, they exhibit quantum effects. But when you start putting a lot of quantum particles together, they start looking more like a classical system. So for example, a tiny electron can go through two tiny slits at the same time, so it exhibits a quantum effect. But we as humans, we are constituted of many, many electrons and many, many quantum particles. We cannot go through two doors all at once, so we're classical beings. So it's the question of whether we can keep increasing the number of qubits and keep this quantum effect present, or whether the system will start collapsing to a classical state. So we still don't know if the physics kind of created a ceiling there that we cannot penetrate, and maybe we will not be able to grow our quantum computers to have millions of qubits, but we will reach some ceiling maybe in the future. We don't know. We'll still need to find this boundary of physics. But so far, you've seen that the number of qubits grow quite rapidly, yeah? Doubling every year. Great. So going back to our quantum adversary that can forge digital signatures, so the bad news, of course, that this applies to all current use digital signatures, all of our favorite ones. And there are two problems for blockchains, going kind of back to what I said in the beginning. Quantum autarky can either steal funds on the honest users' accounts, or it can fork proof-of-stake consensus. It can do both as well. The good news is that there are secure alternatives. We started developing new cryptographic primitives that we know that we kind of are confident are secure against quantum attacks. And let me just give you 2 slides kind of summary at what those alternatives look like. And the pioneer here to just keep an eye on is NIST. It's National Institute of Standards and Technology, US-based institution that pioneered the post-quantum standardization effort. NIST is a prominent body. Wherever cryptography needs standardizes, ends up kind of used all over the world. So in 2016, NIST announced a competition, kind of recognized that the quantum computers might come about, and we need to start preparing for this event if it happens. It announced the competition and asked academics and research laboratories to submit proposals for new secure signatures. And it got a ton of submissions. I was on one of them. And it was really nice to see this collaborative effort of the community trying to come up and standardize new cryptography for post-quantum world. This summer, it announced the signature finalists that it's going to standardize. And next year, NIST is going to roll out the standards. So it promises, so far it's been keeping up with the schedule. So. The finalists are 3 new digital signature schemes, Dilithium, Falcon, and Sphinx Plus. And just to put this number 3 into perspective, the digital signatures that we use today are just 3. We have only 3 standard signature schemes, ECDSA, RSA, and EDDSA. And we also love and use BLS now all over the place. It's not standardized yet. There are some standardization efforts, but this kind of adds a 4th signature. So it's only 4 signatures that we have in our toolkit, and it's really nice that NIST started adding new signatures. We're going to almost double the number of signature schemes that we have in our toolkit, which is great. The bad news is that those signatures are going to be horrible for us. So at the bottom, those are the signatures that we use today. You see, though, they have really tiny public key and signature key sizes. It's just tens of bytes. But these new signature schemes that NIST will roll out standards for are kilobytes in size. And the public keys are really large. So if you ever was worried about the ever-growing state of the blockchain, just imagine how much larger the state is going to be if we were to use post-quantum signatures. So for blockchains, it's not the end of the world. Like several kilobytes, we probably can handle it, but it's kind of nasty. It's not going to be easy to maintain the same performance with these new signature schemes. So the top three are the coming standards. There is an already existing standard that was standardized just in case, because we knew how to do stateful post-quantum signatures. The problem with stateful is you need to maintain secure state, and it's very hard in practice. If you suddenly crash and reboot and you don't know how many signatures you've already produced and you reuse your state, the security is gone. Signature scheme is very hard to use, but in devastating effect that suddenly a quantum computer comes about, there is a signature scheme that can be plugged. And the new promising new signature scheme, SQI sign, that could be nice for blockchains because the signature size and public key size is small, was not part of the competition. It's very, very new, but people keep an eye on it. The problem with that is that signing time is horrible. It's like tens of thousands times slower to produce a signature. So in consensus, it's going to be troubling to have to use it. Maybe for wallets, it's going to be fine. All right, so let me walk you through the transition of blockchain account to post-quantum. So the axis is the time, and we are now in this green region. We're accepting classical signatures only. At some point, when good post-quantum signatures are available, when NIST standardizes new cryptography, we can maybe start accepting both classical and post-quantum signatures. So have this bottom three signatures and top three signatures accepted. And then when we expect the quantum adversary might start to exist close to that region, we can restrict our users to only use classically signed transactions to do key rotations to post-quantum keys, to make sure that first thing, they secure their account against the quantum adversary, so they rotate their key, and then they can transact using this secure key onwards. And then there is this red region where we know the quantum autarky might exist, so we cannot accept classical signatures on our blockchain. So that's a happy path. If our predictions are correct, if we are standardizing good signature scheme just in time, and when we have good prediction of when the quantum autarky might exist. And a happy path, we're going to be in the world like that, if quantum computers are possible. But the main problem with this approach is that what do we do with sleepy users? So if you created your account in this green region, and then you didn't transact at all, and you woke up and suddenly you're in a post-quantum world, and your classical signatures are not accepted. So what do you do? How do you transact out of your classical account? So the easiest approach to do is to introduce a hash somewhere on the path from the secret key derivation to the public key or address derivation, and the hash will act as a shield for the secret key, because hashes are quantum safe. We don't know if efficient algorithm to attack the hashing. So by introducing the hash on the, for example, by hashing the seed to produce the secret key, you are creating the shield for your secret key. And then later on, if the user wakes up and his signatures are not accepted anymore, he can use a Stark proof to show that he knows the seed, to show that he is the owner of the seed, that he knows it, and be able to transact out of his account in the quantum safe account. Because fortunately, we know zero-knowledge Stark systems, Stark proofs are quantum safe as well. Okay, so we can use a hash and a Stark proof to help those sleepy users. But that's something to design for in the beginning. You have to keep this in mind, and if you want to be post-quantum safe for sleepy users, you have to introduce this hash somewhere in your derivation of the secret key. That's important for wallets. And the other problem is that quantum attackers can fork proof-of-stake consensus. So validators currently in proof-of-stake are signing blocks with classical signatures, but if the quantum autarky comes about, it can just go back in history and forge validator signatures from some point, creating alternative blockchain. there are two problems. First of all, quantum autarkia can double spend and can spend funds on the top chain and at the bottom. And also it can confuse the user, as the user will not be able to differentiate which chain is the correct one, what's the correct validator set. So it will cause a lot of disruption as well. So to protect against that, the current most viable solution is to make validators produce quantum-safe certificates. Ask validators to use these heavy, unpleasant post-quantum signatures to sign blocks infrequently. And infrequently just because those quantum signatures are expensive. They're large and they take more time to produce. So we can just ask the validator set when it changes to produce a post-quantum signature certificate on the block before they change the validator set. And you can start with very infrequent signing, but you can put those certificates closer together and ask validators to sign more and more frequently as we are kind of as the number of qubits in the quantum computer grows, and we think we might be approaching post-quantum state. At the end, just having validators sign every block with post-quantum signatures. Okay, so that's the protection you can introduce today to defend your consensus. Okay, so there are two actions for blockchain developers. The first one is kind of easier to roll out. You just introduce the hash on the path to the secret key derivation, and the other is kind of more complicated because you need to implement this post-quantum signature alternatives. There are implementations available, but those are kind of prototype state. But that's something you can also do. Implement post-quantum signatures and ask validators to sign using those signatures infrequently. Cool. So we looked at Shor's algorithm. We just saw how to protect blockchains against that. And let me quickly show you the Grover's algorithm. It also has some implications, but they're not so devastating as for Shor. So Grover's algorithm is for search problems. If you have a function that takes n-bit input, produces 0, 1, the search problem asks you to find x such that f of x equals 1. So classically, you will have to trial possible inputs and do 2 to the n number of steps to figure out where your function is 1. And quantumly, and very surprisingly, it turns out you can do this with fewer number of steps. It's not exponentially fewer steps, but it's still an improvement. So it's 2 to the n over 2. And this was a very exciting result because it showed the separation between classical and quantum algorithms, showing concretely that quantum computers are more superior to classical. And the example here is, for example, finding preimages of a hash function. For some value h, you need to find the message m such that the hash of the message equals the value h. So Grover's search will be faster than classical here. An implication for the blockchain is that quantum miners would be solving proof-of-work puzzles faster. So in order to search d-size space, quantum miners will be spending square root of d time, and classical miners will be spending d time. So quantum miners are going to be faster. So that's something to keep in mind if you're worried about if you're designing a proof-of-work blockchain. That's not a problem for proof-of-stake, of course. And the possible implication for hash, as I've shown in an example, is that you can find preimages faster, but that just brings preimage resistance to match collision resistance, but the hash functions stay secure. You cannot improve on the collision resistance, and you maintain 128-bit security for both problems. So hash functions is really not a problem. Hash stays secure in post-quantum world. Cool. So I am ready to wrap up and give you some thoughts to take home. So the progress in quantum computers is very rapid. With the same pace, we can break cryptography in 15 years, but we might be bounded by the laws of physics. We don't know if there is a ceiling that we cannot penetrate or not. We will see. Maybe we'll see this in the next 5 years or so, whether we can keep up with the growth in the number of qubits or not. And quantum adversaries are indeed a threat for blockchains, but we know how to defend them. So there are 2 action items for blockchain developers that I showed you. One is to protect your secret key by introducing a hash. By the way, Bitcoin, for example, does this naturally because all you see on the blockchain is the address, and the address is the hash of the public key. So you don't see the public key itself. you only see the address, and that also gives you a shield from the quantum attacker. If every time you transact out of the address, you reveal your public key, you rotate to the new key, you're fine. So Bitcoin kind of naturally has this protection, by the way. But that's something you can do for your blockchain. And the other is to protect the consensus. You need to periodically sign with post-quantum signatures. OK, and I think it's a really exciting topic, and it's worth keeping an eye on it. I would say that the quantum mechanics is really hard to understand. And even physicists, they debate on how it should be interpreted and what it really means. And it might be another topic, like similar to AI, where we know how to use it, and it's very useful, but we just don't understand why it works. So it can be the same with quantum computing, that we build quantum computers, but when you're trying to understand why quantum mechanics works, why the quantum computer is actually behaving the way it is, can be like out of the possibility for our human understanding. Great. So I want to conclude with suggesting you some further reading on the topic. There is a classical book, like textbook, on any course. It's called Mike and Ike, informally. It's kind of old, but it covers the whole century of developments, so from 2010. It still remains to be a classical textbook. I think the best way to get started, if you're interested, is to watch online lectures. There was a very nice course by Umesh Vazirani. He was a professor at Berkeley. He did a MOOC in 2013 on quantum computing. Unfortunately, it's not archived on the official website, but you can find YouTube lectures archived by some enthusiasts. I really encourage you to follow Scott Aronson, and he has a lecture notes published. It can be read as a book as well. It's available online. It's a very pleasant read. You don't need to know a lot of math to kind of follow. And Scott Aronson's blog is the best way to kind of see what's the recent news in there. None of that will go unnoticed by Scott, and he will comment on that and give his thoughts. They can be controversial, you may disagree, but that's a great resource to just keep an eye on what's going on in the field. Fantastic. I think that's all I have in this quarter slide there.
Hi, Emmanuel from Shield. Awesome presentation. So you mentioned that the whole study that basically talked about how many qubits would be necessary to crack the RSA certificates, that was like a dispute and invalidated. So I'm wondering what goes into those calculations of like how many qubits are required to crack a specific system, and how trustworthy are those calculations today?
Yeah, great question. So typically, the algorithm is described, and you just look at how many qubits it needs. So it's a pretty easy number to just figure out just looking at the algorithm. What makes it a little harder is that typically those algorithms are designed for logical qubits, assuming the system performs without any errors and just performs correctly and does the operations that you want there to be done. But unfortunately, in practice, that's not the case. The qubits are very, very noisy, and they err all the time. You need to repeat the computation many, many times, or you need to apply error-correcting codes. So a lot of calculations about what the actual number of qubits you need will go into figuring out what error-correcting scheme you need for that algorithm. So that's not such a trivial problem if you really need to figure out the number of physical qubits. Yeah, but that's a great question. Error correcting is definitely something quite painful for the developers of quantum computing there.
Yeah, thank you.
Thanks for the great talk. I'm Nikita from Chain Patrol. I had a question around, you mentioned that the quantum system will try to enter into like a lower energy state, so it's useful for like escaping these local minimum. Mm-hmm. Does it have like a limit on how far it can kind of like travel or move? Is there like a certain, like it won't jump further than like a certain barrier? So like, yeah, well, that's my first question. Is there a limit on that?
Yeah, that's a great question. That's indeed the main critique of those computers, is that if you other local minimum that's lower is too far, the system will not penetrate that barrier. So it only, it's not going to work for finding global minimums of any function. It's only kind of will be able to penetrate small barriers. So
Yeah, for shorter jumps, basically.
exactly, for shorter jumps.
Okay, yeah. And then just one more question is around, when dealing with digital, like when you're doing like arithmetic for, I don't know, like machine learning or something, you always have to do all these tricks to like get rid of like floating point errors. But here it seems like it's more like you can get any value in between. So does it get rid of like basically like floating point errors and, like overflows and that kind of stuff?
Oh, great question. Actually, it's very interesting you ask that because indeed, you may think the qubit is, you can kind of encode, it's a superposition of 0 and 1 with some floating point coefficients, that's true. And in principle, you can encode a lot of information into each of these coefficients because those are real numbers. But in practice, the way you extract information from the qubit is you measure it. And when you measure it, it only collapses to one of the states with the probabilities that are defined by this x and y. So you only get 0 or 1. In fact, it's very difficult to get a sense of the values of x and y if you don't know them. So if you want to figure out the floating point number, you can only, x or y, you can only figure it out with certain precision.
Okay.
You will not have infinite precision there. So
Okay,
dealing with floating numbers is still tricky.
That's really interesting. Thank you.
Sure. I know.
So if I remember correctly, like from comp sci classes forever ago, where they have you prove lots of, or if a problem is non-polynomial or a lot, often the way you do this is you do like the NP reduction, where you sort of take a non-polynomial problem and turn it into another problem, and you can sort of say, you eventually come to the conclusion that like any non-polynomial problem can be represented as any other non-polynomial problem, right?
Yeah.
So does the existence, and you can sort of like use the individual non-polynomial problem as sort of like an inside step, right? And you do that in polynomial time. So does the existence of something like Shor's algorithm, which is like or classically like a known non-polynomial problem, mean that you could take any other non-polynomial problem, right, and represent it as Shor's or as a factoring problem, right? So does just the existence of Shor's being solved in polynomial time in a quantum computer mean that like you can solve all of the non-polynomial problems in polynomial time on a quantum computer, or is there like some quantum stuff that makes that not possible?
Yeah, great question. Shor is kind of this, factoring is kind of the special problem that doesn't have a lot of problems reduced to it. It's not like NP complete or something, and it can well be that we figure out suddenly an algorithm to classically solve factoring quickly. So, for example, for primality testing, for a long time, we didn't know a deterministic algorithm to do primality testing, and we thought this is an exponential, this requires super polynomial number of steps, and suddenly there are like, I think 2 undergrads from India kind of figured out an algorithm to do deterministic primality testing. So I think it's the same kind of might possibly happen to factoring, that we kind of figure out an algorithm, and it will not collapse, NP to P or collapse any complexity classes, if you're asking about that. But it's interesting, though, the quantum algorithm that breaks factoring, in fact, underneath what it does, there's an efficient way to find periods of periodic functions. So any problem that can be reduced to finding periods we'll be able to solve it using a quantum computer in polynomial time. So for example, discrete log reduces to finding periods, and factoring reduces to finding periods. And there are other more generic problems that reduce to it as well. But I don't think there are many useful problems that we know of yet that will be able to use Shor.
So then the hope is that like finding periods is not a real non-polynomial problem, that there is like hiding somewhere like a classical solution.
Yeah, definitely. So it's possible that we have a classical solution for that problem, but so far we only know how to do it efficiently on a quantum computer.
Cool. Thank you.
Hey, Brandon. Thanks for the talk. That was really, really cool and futuristic, so I appreciate it. It seems like the framework we're using here is that in a post-quantum world, we have an adversary with a quantum capability, and the network doesn't have quantum capabilities, and so we're trying to like defend information using time with more advanced signature algorithms. Right. Are there any thoughts around like, what about if the good guys also have quantum computers? Are there like physics properties that we can use aside from information and secrets to make things quantum safe?
Yeah, that's a great question. I didn't touch on that field. That's a completely new field of cryptography. People are trying to design cryptography specifically for quantum computing. It's very exciting. There are lots of new developments there. It's even more futuristic, of course, there, but it's definitely possible to design new cryptography there. Well, if we're in the setting that I was describing, where quantum computer is cloud-based and we have classical machines connecting to it, we still will probably need classical cryptography, so it's going to stay with us in this post-quantum signatures we're going to still be using. But indeed, the quantum computers, to talk to each other, they might use some more fancy stuff. I think it's very premature kind of to see the algorithms there, but there's definitely some academic works there.
Cool. Yeah, thank you so much.
Yeah, sure.
I understand this might be a bit more science fiction, but is faster than light quantum entangled communication? I'm curious if there's been any further developments in that direction.
Yeah. This China experiment that I was talking about briefly, that they established a secure connection between Beijing and Vienna, I think, was the way it works is the satellite was producing entangled photons, that it was shooting those to two on-Earth locations, and they were measured there, and that's how you get the same. Well, it's more complicated than that, but that's already kind of was done. And entanglement, in general, was demonstrated already quite a few years ago. But the challenge right now is to grow the number of qubits that can be entangled and maintain them in the entangled state. Because these quantum systems, they're super fragile. The moment you touch it classically, it kind of collapses to a classical state, and the entanglement is gone. So it's really the challenge of maintaining entanglement of a large group of qubits.
So would you say like quantum teleportation is something that might be possible then? Or,
quantum teleportation?
Teleportation, where you can actually have directed data.
Yeah. I think it was demonstrated definitely as well. So it's not that you are communicating with a speed of light larger than the speed of light, but the way it works is that I can transfer my qubit to you if we have also a classical channel of communication. So without physically sending you the qubit, you will be able to get the same qubit as I have. So not the same, but I will destroy my qubit and recreate it kind of on your end using a classical communication channel. So you need still this classical communication channel to just talk to each other, but quantum states can be teleported. They cannot be copied, but they can be moved around. And they can also, there are some interesting transitive properties, like you can teleport to another guy if I teleport with you and you teleport with him, you can teleport your qubit. So there are some transitive properties you can do as well. But yeah, that's definitely very interesting.
Thank you very much. Really fascinating.
Hi there, my name's Murat. Fascinating talk. Thank you very much. I have a question about this kind of the cold 0 Kelvin requirement of quantum computers. Would it be feasible to have quantum computers in space that compute things, and then maybe we interact with them through Earth, and they maintain I guess a more manageable environment over there, and it's de facto 0 Kelvin?
Yeah, I agree. That might well be our future, indeed, because you're right. We have cooling for free in space, and there are no vibrations. So, indeed, I'm not aware of experiments in that direction. But I bet there are some trying to study quantum effects in space. But that's true. The more satellites are being launched, the more likely we have more compute power in the sky, and maybe those satellites can talk to each other using these quantum channels, establishing secure links of communication. I think that might likely be.
So then we can imagine a future where maybe we don't have chips in our phones, or they have very lightweight chips, but it's kind of a mainframe type of architecture where things are kind of in space, and we're able to use quantum computation for that.
Yeah. Exactly. Yeah.
Thanks for validating the feasibility. If my startup here for some reason doesn't work out, I might pursue something in space like this. Thank you.
Fantastic. Thanks for the question.
Hey, it seems like there have been some issues with the post-quantum algorithms in the NIST competition. Are there further concerns that attack vectors might be found? Is there anything in particular about post-quantum algorithms that makes them more susceptible to attacks?
Yeah, great question. The main problem, of course, that this cryptography is newer and it's less studied. It's really nice that it's a collaborative effort and it's very massive, so it gets a lot of eyes of people trying to break it, analyze it. I would say that those 3 signatures that NIST has chosen are very conservative choices. 2 are based on lattices, and we know this is a very well-established, long-standing assumption as well, so we have good security, good confidence in its security. It's unlikely that we're going to see any problems with those schemes. And the other one, Sphinx Plus, is a hash-based. It's super well studied. It's only based on hashing, nothing else. There are no other mathematical assumptions. So that's the most conservative variant. Unfortunately, it's the less performant. Everything is much slower with Sphinx. But I have good confidence in the schemes that NIST has chosen. I bet NIST will choose more because just the signature sizes are not satisfactory. In fact, it's opening another call for proposals, I think this summer, to encourage people to think of more signature schemes with shorter signatures. So we'll see what goes in there. Maybe some more fancy assumptions have to be introduced that we'll be less confident about.
Thank you.
Lera, I have one more question if there's no more from the group. So you had a slide on like the physical design of quantum computers. How it's actually just like a chip, and the rest of it is the cooling infrastructure.
Yeah.
And because of that you don't expect that we'll ever have quantum chips within laptops or even phones. Is that like a physical limitation and a certainty going forward, or do you think that it's possible that similar to the way that other computers have gotten smaller and smaller over time, that the same thing could happen with these quantum chips?
Yeah, good question. Maybe, possibly, that we have a small, tiny cooler inside our phones that will be able to maintain this pristine environment. The vibrations are also a problem. I think probably technologically, there is no physical limit to why we have to have a cloud-based quantum computer. Maybe it's just going to be that way for a long while until we kind of figure out how to miniaturize everything. But that's true. Possibly, at the end of the day, we're going to have quantum computers on our phones. That's true. No, I am not aware of any physical limitations.
Thank you, Lera.
Yeah,
that was great.
Thank you.